Let's go over a general outline of how to apply the principle of conservation of energy to solve problems. Remember that the work-energy theorem says when there are no non-conservative work done by any forces, the total mechanical energy of a system is constant, or the change in energy between any two states is zero. To apply this, we need to think about what goes into the total energy of a system, and in general, it's composed of some kinetic energies and some potential energies. Whatever types of energy the system possesses, we have to add them all up together to get the total mechanical energy. Now, the amount of kinetic energies you have and the amount of potential energies that you have to consider depends on the problem, how many objects are involved, and how many forces, conservative forces, are involved. Typically, our kinetic energy terms would involve one term for each object, and the kinetic energy for that object would be its mass times its speed squared times the factor 1/2. If the problem involves a gravitational force, then each particle or object will get a gravitational potential energy that is equal to its mass times the acceleration of gravity times its vertical coordinate y. If there are any springs in the problem, then each one will contribute a potential energy equal to 1/2 times the spring constant times the stretch of the spring squared. If there are other types of forces in the problem, such as electrical, magnetic, or arbitrary potentials, each one of those will contribute its potential energy as well. So let's look at a classic example of where we would be able to apply conservation of energy to get a really powerful and efficient solution. Anytime an object rolls across an inclined surface, or moves or slides with low friction, this is a place where we can apply conservation of energy because there is low friction, so there's not any non-conservative work. Let me draw a diagram. So what I've drawn here is a curved surface, and the intention here is that there's some object with low friction that can move back and forth any place along this surface. So the classic example is a roller coaster problem, or a train on a track on a hill, or a bike on a hill that's going to roll down the hill due to the effects of gravity. So the way to approach this using conservation of energy is to use the principle that it's constant. So what we do is we look at the total energy at different places. I'm going to label several points on here. So I've labeled 5 points. These points are they have no particular importance. I could have put them anywhere on here. Conservation of energy will work just the same. My object has a mass which I'm going to call m, and at any particular point, let's look at, say, location B. This cart would have some speed, which we would label as VB. And at all the other points, it would also have some speed, V with some subscript. And these may all be different, or some of them might be the same. So that basically handles the kinetic energy at each point. For example, at location B, we would have 1/2 times the mass of the object, which doesn't change from point to point, times the speed of the object squared at that location. For potential energy in this roller coaster situation, we need to think about what forces are active. Well, we know from previous chapters that an object on an incline feels a force of gravity, feels a normal force. It doesn't feel any other ones in this example because we're saying that it's frictionless. The normal force doesn't get a potential energy assigned to it because it never does any work. The gravitational force, however, is always pulling on this cart in the downward direction, so there is going to be a gravitational potential energy to consider. It will depend on the y-coordinate of each location. To use gravitational potential energy, we always need to set a reference point or a reference level, some place to act as y equals 0, basically an origin for our coordinate system. All of the other locations can then be measured for their y-coordinate. I've tried to draw this dotted line for y equals 0 so that it doesn't coincide with any of the labeled points, because it doesn't have to. So with these labels for the y values set up for each location, we can then form an expression for the potential energy at a given location. For example, at location B, the potential energy would be m times g times yb. Notice that there's nothing particularly special about y equals 0. This curve surface could easily go below y equals 0. There's no problem with that. The potential energy would become negative, and there's no problem with that at all. So let's look at what the total energy would look like then. We've been kind of drawing these formulas for location B, so let's continue. The energy at location B would then be the sum of all kinetic energies and potential energies in the system. We've only got one kinetic term and one potential term, so this is the expression for the total energy at location B. For the other locations, we have a very similar expression. The only thing which is different is the subscripts for the velocity or speed at that location and the y-coordinate at that location. So our method of solution, depending on what we're asked, would be to form these expressions for total energy and then apply the principle of conservation of energy, which states that each one of these energies, no matter which point we choose, should equal the same value. So what we can tell from this is that the speed may change, the vertical position may change, but they have to change together in a way that keeps the total energy constant. Let's clear off this board and write an example with some numbers. I've left the diagram up here. Let's do an example problem where we try to relate what is happening at location A to what might be happening at location B. So I'll first write out conservation of energy comparing these two locations. Let's assume that we've been given the following information about this cart on a slope. The goal of this problem is to find out the speed of this cart when it is at location B. So before just plugging in, since I don't have the mass, I'm going to do some algebra on our conservation of energy equation and try to solve it for VB first. So to solve this now, I just have to take the square root of both sides. But remember that when I take square roots, I lose information about signs. This formula only tells me what the square of VB should be to conserve energy. So it could be a positive answer for this speed, or a negative answer for the speed. That reflects a general property of conservation of energy problems, is that they only relate 2 points to each other. They don't tell you really about the direction that the motion goes, how long it takes, or things like that. If this object was at location A, say rolling down the hill at 2 meters per second, if I assumed that, then it would make sense to choose the positive value here, VB, continuing to go down the hill. But the other assumption is not wrong. If I assumed that I was told in the green marker there that the object was moving still up the hill at location A, then at location B, it would be correct to conclude that it was moving up the hill at B also, right? So if we plug in the numbers to this, we have 3.5. Oh, excuse me, this is VA squared, just like it was in the line above. If we plug in the numbers 3.5, 0.5 to YA and YB, we plug in VA as 2 meters per second. We find out that conservation of energy says that VB should be positive or negative 7.93 meters per second. All right, let's do a little check if that answer makes sense. If we assume it was moving downhill at location A, then by the time it gets to B, it's moving even faster downhill. So that's reasonable to see a speed up. Now, these equations for conservation of energy, you only get one because you're only equating energy to energy. There's no vector components. There's not a different one for each object. It's only like a totals game. But look at the power of what we've got here. We were able to relate this position to this position, and we could have easily related it to location C or D or F. The mathematics would look exactly the same, except for different subscripts. Also, it doesn't depend at all on the actual shape of this slope. This curvy slope doesn't matter at all. We were just able to look at one location, another location. We could easily apply this same equation to location C, D, or F without any additional difficulty.